Everybody for joining us for the first Survey UCF Brown graduate seminar. This is going to be an introduction to the science and exploration of Phobos and Deimos. And basically this is going to be run as a graduate capstone class, but we're going to do some interesting things. Basically what we want to do is discuss cutting-edge science that can direct and inform exploration, and take advantage of the Survey Adobe Connect system so that we can bring in the top people in this field to speak to their expertise and allow a broad audience to interact with them. And the whole point is to identify the extent of our knowledge and also define the gaps in this knowledge. As I said, it's organized as a capstone graduate seminar. I'm here at the University of Central Florida. I have my University of Central Florida graduate seminar class here. There are several other graduate seminar classes going on simultaneously, also at Brown and several other places. And what we're going to do is share the content. We'll also have local content and local discussions. But the core of this class is going to be what we can receive over the Adobe Connect system. Now I direct your attention to the website in red on the screen. We have the readings, the schedule, and also bios of the speakers available on this website. And remember that these Adobe Connect broadcasts are also going to be recorded and available over the Ames Survey system. And so this course is going to be a mix of the following. It's a series of 13 core lectures taught by the experts in Phobos and Deimos. And for several of the various seminar course classes in different universities, there's going to be local content, which will, in the case of UCF, is going to be a critical review and discussion of the core lectures. And of course, this core content is going to be, as I said, broadcast Mondays at 3 p.m. Eastern, with about an hour lecture and 30 minutes for discussion. As I said, these are going to be recorded. Now, a few words of caution about these recordings. Everything gets recorded. The chats, the online chats get recorded. The things that are said get recorded. And so if you don't want what you say or what you chat to be recorded, then you need to do private chats and be a little bit careful about what you say. The audience has a role, and I'm putting a requirement on the audience of this operation. Critical and lively discussion of each lecture is key. And I want to encourage the remote audience to ask questions or to make comments. It doesn't matter. Or propose some alternatives to what you hear being said. The way you'll have to do this is via the chat box on the Adobe Connect window. There are far too many people online. How many people are online right now?
76.
76. So the size of the remote audience limits the opportunity to directly speak. We have a moderator who is going to monitor the chat box and relay questions. If you have a burning question that you want to try to insert during the lecture, please put it in the chat box. That's okay. That's permitted. It will be up to the moderator to whether this will be inserted or not. But the whole point is to have an interaction and a discussion with the experts in this field. And clarifications, critical points, need to be addressed. And I urge the audience to do that. That's a requirement that I levy on the audience, and I want to see that the audience responds. For my class in this room, one of the things that I levy upon them is they need to ask good questions. That's critical to being in the class. Overall, what we're interested in is strategic knowledge gaps. Now I'll define that. They represent gaps in knowledge or information required to reduce risk, increase effectiveness, and improve the design of robotic and human space exploration missions. I lifted that from the Small Bodies Assessment Group document about small bodies and moons of Mars strategic knowledge gaps. Part of the process of reviewing what we know about Phobos and Deimos will be to better clarify what we don't know and what we need to know. And that's one of the requirements that I'm levying on my class here, is to better define and describe the Phobos and Deimos strategic knowledge gaps. Now, to some extent, they've been, a goodly chunk of them have been written down, but usually they're one-liners. And we need to be more specific and expand upon those one-liners to be able to be more useful. Also, try to identify strategic knowledge gaps that your forebears have not identified. And that's an important process, part of the process that we're going to go through during this semester. So the core lecture schedule is up on the slide right now. Basically, you can break this up into 5 major themes. The surface and morphology. We probably know the most about this. And so there'll be 4 lectures. Nico will talk about the age and cratering history. Ken Ramsey will talk about the formation and effects of the Stickney impact, which is by far the most striking feature of these moons. Another striking feature is the origin and the characterization of the grooves, and John Murray will address that. And finally, Sasha Basilewski will talk about the geology and the geomorphology of Phobos and Deimos, and he will win the Time Zone Award for covering the most possible time zones between Ames and, I believe he'll be talking from Moscow. So, next we'll talk about composition and mineralogy. Rifkin and Klimka will talk about the ambiguity of compositional data. Chris Hurd will be holding forth on the properties of the meteorite analogs. Looking at the origin, we'll look at, Joe Burns will look at the dynamical evolution of Phobos and Deimos. And Robin Knupp will address the possibility that they were co-accreted, produced by a giant impact on Mars, and other possibilities. And what they'll do is go over the constraints and the probabilities of different origin scenarios. Because the origin of Phobos and Deimos is still highly controversial. We'll go into the environment of Phobos and Deimos. And so Phobos and Deimos are in a unique environment from a gravity point of view. They're deep within the Mars gravity well. It's kind of a unique environment for a small body. That produces some interesting effects, not only in dealing with the microgravity, but also tidal effects from Mars. Space weathering, regolith, dust. Carly Peters and Mihai Harani will address those issues because this is a dusty environment. Being inside the Mars gravity well allows you to reaccrete a lot of the ejecta that would normally be lost on a small body like this. So fundamentally, these things are probably going to have a dustier, more finer grained regolith than a small body of equivalent size that's an asteroid. And also the future. What are you going to do with Phobos and Deimos? Phil Metzger and Rob Mueller are going to address in situ resource utilization at Phobos and Deimos. And also Mike Gernhardt will then wrap things up with Phobos as an exploration destination and a possible base for Mars exploration. So I hope you'll enjoy this adventure. I think it's an adventure at the cutting edge of where we are in small body science with Phobos and Deimos. And it'll help us define the parameters of what we need to learn to make smart choices in the exploration of these bodies. So the advantage of being the introduction is I get to talk about things at a very high level and also throw in a couple of totally off-the-wall comments, including a bit of history, because I like history. And so Phobos and Deimos were discovered by Hall of the U.S. Naval Observatory back in 1877. What he did was he made a visual discovery using one of the biggest refractors of the time. And essentially he had a micrometer that he was able to block out Mars in his field of view and a lot of the Mars shine. And once you do that, Phobos and Deimos can be seen. Although this is a 1988 image, and as you can see, they're not terribly bright. It is still a remarkable achievement to see these things. And it turns out that for a long time, up until relatively recently, until the age of CCDs, the eye was a better instrument for doing this sort of work, because the eye has a much better functional dynamic range than things like photographic plates of the old days. These days with the CCDs, what you do is you essentially block out the Mars glare pixel by pixel. Being the discoverer, he got to name them, and I'll talk about that in a minute. But basically, this led to some pretty solid science. It allowed for the accurate determination of the Martian mass, and then, of course, its density. It provided the implication that moons were pretty common around other planets. What you had seen before was a moon around Earth, which you knew about, and Galileo saw moons around Jupiter, and you had moons around Saturn. This was actually an implication that even for other terrestrial planets, moons were relatively common. Turns out that none of the other terrestrial planets besides Mars and the Earth have moons, but it was an interesting piece of science for the time. And of course, the close orbit of Phobos meant that you get 3 moonrises per Martian day. And aside for this is that the major feature on Phobos, Stickney crater, was named in 1973 after Hall's wife, Angeline Stickney Hall. And she was quite a character. A lifelong suffragette and very active, an accomplished mathematician. She assisted Hall quite a bit in the determination of orbits. But, and I will quote this from the Naval Observatory website, however, she demanded a man's wage while she assisted her husband in his computations. When he refused her, she refused to continue that work. She quit. I like this woman. So Hall named the moons after mythological associations of the primary about Mars. Phobos can be translated from the Greek as fear or horror. Deimos, terror or dread, are the twin sons of Mars, the god of war. Now remember that Mars is the Roman name for the god of war. Ares is the Greek name. But they're basically the same person. They borrow between the two. And Mars was messing around with Venus, goddess of love and beauty, and that's where the twins came from. I should note that when you start reading this, you recognize just how dysfunctional Greek mythological families are, because Venus was married to Vulcan. Venus is also claimed as an ancestor of Julius Caesar. And it's not like Phobos and Deimos are really the only choices for Mars's companions. There were a lot of options. He had a sister Eris, which is the goddess of discord. His daughter Adrista, which is the goddess of revolt and just retribution. And then you've got the demon of the noise of battle, demons of acts of manslaughter, or any one of his 100 children by about roughly 40 consorts. He had 9 other children by Venus, for instance. So talk about dysfunctional families. Anyway, I like that. Hall was preceded in this discovery by Jonathan Swift, 151 years prior to his discovery. There's in Gulliver's Travels, they talked about the Lilliputian astronomers have likewise discovered 2 lesser stars or satellites, which revolve around Mars. Thereof, the innermost is distant from the center of the primary, exactly 3 of his diameters, and the outermost 5, which is not bad. Not bad at all. And of course, Jonathan Swift had no idea about this. But one of the reasons that Hall was looking was that the general scientific tenor of the time thought that there should be at least moons around all planets. And that the reason you hadn't seen them before was that they're probably small moons. And so he was looking specifically for small moons because that was a current idea rattling around astronomy at that time. And so physical properties. Jonathan Swift said 3 Mars radii. Phobos is actually 2.76. Not bad. Deimos is 7 Mars radii out. Phobos is roughly 23 kilometers in diameter. Deimos is roughly 6 kilometers in diameter. They're dark. If you would look at them, they would look black. They're kind of charcoal briquette black. And low density. So Phobos has a bulk density of 1.87, and Deimos has a bulk density of 1.47. This is in the range of a dirt clod. It indicates probably a very porous object of some fashion, and we'll talk about that some more. Very low surface gravity. We'll talk about that some more. Very modest escape velocity, 11.4 meters per second from Phobos, 5.5 meters per second from Deimos. Most of us could leap off Deimos without any problem at all. Orbital period for Phobos of 7 hours and 40 minutes. So you can easily squeeze in 3 moon rises and sets in a Martian day. Deimos has an orbital period of 30 hours. Both are tidally synchronized to Mars, so they always present the same side. Both have nearly circular orbits with very low inclinations, and that's an important part of an important clue in looking at the dynamics and the possible origins of these bodies. Deimos is just beyond Mars geostationary orbit. Mars geostationary is about 20,000 kilometers. And so Deimos is actually gaining orbital energy from its tidal interactions with Mars, and so slowly precessing out. Phobos is losing orbital energy and slowly decaying in. And various people have thought that you'll eventually have a collision with Mars roughly in the 40, 50 million year range. Something to look forward to. Density. So as I said, very underdense objects. If you look at the different meteorite analogs, the volatile-rich carbonaceous chondrites, or GAY, or the average CM, have substantial porosity and get roughly in the range of Phobos and Deimos. But for Orgay, for instance, you need 35% porosity in that meteorite in order to put it in the range of Phobos and Deimos. The average CM has about 2.2 grams per cubic centimeter bulk density, but it has almost 25% porosity in that bulk density also. So to get down to the densities, the bulk densities that you see in Phobos and Deimos, for any sort of reasonable solar system materials, you're going to have substantial porosity. These guys are probably rubble piles. And the question is whether you have how much low density material is in that mix already. Because things like phyllosilicates, clays, carbon compounds are fairly low density. But when you get more iron-rich silicates, like what you find in Martian meteorites, the average SNCC, the average SNC, or the average L-chondrite, you get substantially more bulk density. And in order to get down to the range of Phobos and Deimos, you need a very porous object. You need a lot of large-scale porosity, macro porosity.
We have a porosity question. Would you like to?
Sure. A porosity question.
What did the latest observations suggest for modeling bulk density as a combination of volatile content, i.e. H2O, in conjunction with porosity instead of just porosity?
So to paraphrase the question for those that didn't hear it, what are the latest thoughts on modeling water content along with just voids? The problem you have with water is that water still has appreciable density. It's 1 gram per cubic centimeter, or 0.93 grams per cubic centimeter if it's ice. And so you need a whole lot more porosity if you have a component of water ice, because the water ice is actually contributing to mass, contributing to bulk density. And you need substantially more porosity then. I hope that answered the question. So I'm going to move on. Albedo. People that have looked at the spectra consider the spectroscopy to be roughly like a D-type asteroid. But D-type asteroids have fairly unremarkable spectra because they are flat and they are dark. They're hard to see very many features. That doesn't mean we don't see any, but you see things that look analogous to D-type asteroids. D-type asteroids tend to be much darker, will tend to be darker than Phobos and Deimos. So the average for D-type asteroids is roughly about 4% albedo. Phobos and Deimos are up around 7%, which suggests, if they are D-types, that it would be that they must have an admixture of lighter materials. Mars is far above this plot at 7% albedo. The Mars meteorites, on average, are running about 35% albedo, although it varies quite a bit. So you have some information from albedo, but of course it's not conclusive one way or another. Gravitational environment. This is a unique environment for small bodies. Generally, you don't find small bodies deep in a gravity well. And so they have low self-gravity. So for Deimos, you should be able to escape with a bike and a ramp. This is the gravity well to scale. And for Phobos, you could probably easily throw a baseball to escape velocity. But remember, you're still deep in the gravity well. So what's going to happen is that low to moderate velocity ejecta is going to be trapped in that gravity well and retained. And some of that should be reaccreted. And I think one of the reasons why you have a substantial regolith on Phobos and Deimos is that you have this process of reaccreting ejecta material. So there's evidence for a thick, loose regolith. If you look carefully at the Phobos images, you see lots of evidence for loose material and surface movement. The top picture shows a flat-floored crater, which is indicative of perhaps the bedrock, perhaps a solid layer that's about 200 meters down through the regolith. You can also see the slope failure of loose material that has slid down an impact crater. Excuse me. And on Deimos, Deimos is a much more subdued terrain, and you have evidence of dusty streaks. So you can just barely see these things in the image. There's on one side of these little craters, the large craters at the top and the middle, you see that it's slightly lighter on one side than the other, and that's been interpreted as a dusty streak. I'm not sure I believe that, but That's an interpretation. I think it's safe to say that both objects have a substantial regolith, that the regolith is probably pretty dusty. And of course, we have the most spectacular views in the solar system. From the surface of Mars, Phobos is about half the apparent size of the sun. And remember, it comes up 3 times a day. And so it's around a lot. That's Phobos occulting the sun. From Phobos, the apparent size of Mars is 42.5 degrees. That's 6,400 times larger than the moon from our Earth. So a spectacular view. And as you can see here, this is Phobos in the lower image and Mars in the background. Just a spectacular view. Origins. A couple of different ideas, and we're going to look at this in excruciating detail. So, captured asteroid. The evidence for that is the low density, the low albedo, the spectroscopy that suggests a D-class asteroid, similar to what you find in the outer asteroid belt. Possible source could be planetesimals that were scattered by Jupiter. The problem is that capture requires that you lose orbital energy within the Hill sphere, and quite a bit of it. The other problem is that the low inclination and circular orbit is very hard to achieve with the kind of tidal evolution that Mars can produce. And both Phobos and Deimos, being in that low inclination circular equatorial orbit, is a tough requirement to meet. And Joe Burns will be talking about that much more extensively. One of the plots here is the size of the Hill sphere of planets. And Mars does not have an insignificant Hill sphere. That's the area of gravitational dominance by that object. But capturing it requires a lot of effort. Other possibilities, form from Mars ejecta. You look at the albedo of Phobos and Deimos, it's on the high end of primitive bodies. It does have shallow absorption features, and the dynamics work a lot better if you are formed from, say, ejecta. The source would be Mars' early heavy bombardment, and Robin Knupp will address some of these issues in her talk. Problems? Well, the albedo is low. The Mars material content appears low because it's very hard to make bright stuff dark, and you require an extra impulse to get and stay in orbit. But, we have our moon probably formed by a large impact, so certainly it's not impossible. Accreted in place as a consequence of planetary formation from nebular material is another thought. Again, the problem here is that the material that you would be accreting would tend to be fairly high albedo, and the albedo is pretty low. So we'll address these in much more detail in later lectures. Right now, I'm just going to show you some pretty pictures and detail some features. So Phobos, characteristics of Phobos. You see the very large impact crater of Stickney on one end, but also you see these grooves and pits. They are a dominant feature on the surface. So this is a great picture detailing grooves, and you can see they run in different alignments, and then you have these chains of pits. And there's a number of thoughts as to these formations. We'll address those. Ken Ramsey will look at the formation of Stickney. John Murray will talk about the pits. We'll have plenty of discussion of these things. But as you can see, Phobos is a fairly rough surface because almost everywhere on the surface, you've got these grooves and pits going in different orientations, meeting in small bodies. more grooves, more pits, more chains of features. More pits along this way, and many more grooves. Again, I have evidence of the thick regolith. The flat-floored craters, the slope failure in the loose material, all of this points to a thick and relatively unconsolidated regolith. Of course, sometimes you get false color. If you looked at Phobos and Deimos with your eyes, you would definitely not see this. But if you stretch your images, you get some units that are somewhat bluer and some units that are somewhat redder. And the result is gorgeous. Deimos. Deimos is much more subdued terrain. Much smoother. Many fewer landing hazards because there's lots of flat space on Deimos. It's almost as if the whole thing has been blanketed by a dusty layer and the terrain has been smoothed out. And we'll talk about that more in the other lectures. The primary feature on Deimos is a hemispheric-sized crater on one side. And that's a substantial feature and also a substantial constraint on its evolution. If you look at it in detail, and we actually had the Viking spacecraft did a relatively close pass of Deimos, you can get down to objects that are a few meters across, and you see a very smooth surface, even at the meter scale. See a few blocks, a few relatively fresh craters, but most of it's subdued. Most of the craters are relatively filled in, relatively relaxed. You find boulders on both objects. So on Phobos, this is the rim of Stickney. You see groups of boulders. Again, the scale is such that these are fairly large boulders, but you're probably going to find smaller ones. And the same thing with Deimos, a few boulders. Compare that to Eros. Eros has lots of boulders. Eros is much rougher at the tens of meter scale than either of these objects. Spectral data, question? Do you prefer to take them all at the end or take some as you go along? I can take some as I go along.
Okay, well, this one's about specifically the images we were just looking at from Leslie Gersh. At the resolution and perspective of the images, the landslide deposit appears to be too small to fill in the apparent volume of the landslide scar. Perhaps some of the material reached escape velocity, or question mark?
To repeat it, if looking at this slope failure, this landslide, it looks like the material is too small a volume to fill the volume of the slope failure. Perhaps some of it reached escape velocity. It looks to me like it was initiated by this impact crater. So it is possible that you've lost some portion of it from ejecta from the impact crater. On the other hand, it's really hard to tell whether the volume would be the same. I would have to, I don't want to hazard a guess as to whether there's enough volume there or not. Coming from, after spending many years in Southern California and looking at slope failures like this, I found that it's hard to correlate the two. It may also be that the slope failure is a little bit more compacted than the stuff that that was making up the crater rim. So hard to say, but it's a good point. Spectral data. We've looked at this as carefully as we can for evidence of hydration features. If we have a 3 micron band, it's going to be limited to less than 5 or 10%. CRISM data sees a weak 2.8 micron feature. So perhaps don't see any 1 or 2 micron features, but a weak 0.65 micron feature. And so that's consistent with desiccated iron phyllosilicates. Or maybe iron oxides or nanophase iron particles embedded in a neutral matrix. So this isn't, the best spectral analogs again are red low albedo asteroids, metamorphosed CI and CM carbonaceous chondrites. However, nothing is very definite right now. And we will certainly go into this in great detail and look at the best possible data. If you do have phyllosilicates, if it's like CIs and CMs, those tend to be very phyllosilicate rich and relatively low in olivine and pyroxene. Olivine and pyroxene tend to have fairly strong absorptions. So if you have a lot of it, it's relatively easy to see. But of course, you can suppress that with lots of opaques and lots of fine-grained things like carbon compounds. So maybe yes, maybe no. So why go to Phobos and Deimos? You can look at these as stepping stones for Mars. You can get to Mars space and start learning how to operate in Mars space without the major risk factor of dropping into the Mars gravity well. They're a source of potential resources, depending upon what their origin is and what's available. So the low albedo suggests it might be rich in volatiles. Even if it's not rich in volatiles, it's going to have a lot of other potentially useful minerals. You can use these things as basis for surface exploration. So you can use the local materials for shielding to shelter from galactic cosmic rays or from radiation from the sun. And also this can support telepresence and remote surface operations. And the nice thing is that the two-way light time lag for Phobos is something like 40 milliseconds, which is actually a lot less than I'm dealing with looking at my own reflection in the screen here. So that would allow a telepresence for operating experiments and rovers on Mars. That would essentially be real-time driving. It would allow you to do a lot of other science that is not enabled by the current setup of essentially days of latency between commanding, moving, recognizing and processing where you've moved to and what you've done. So what sort of in situ resources are available will depend upon what the origins and mineralogy of these things are. And we fundamentally don't know yet. What we want are fuel, consumables, manufacturing feedstock. Depending upon the origins, you might have things like phyllosilicates and water ice. Carbon compounds, but those are big question marks. What you'll certainly have is silicates. And silicates will yield oxygen and metals because you can break apart the silicate tetrahedra, and silicates are dominantly made of oxygen. You can find iron, you'll probably find iron oxides and iron sulfides. And so that's oxygen, sulfur, and metal. The regolith allows you to build shielding for crew habitats. You can also use this as a feedstock for additive manufacturing. And ask yourself what can be made out of the regolith. Things like heat shields, lifting bodies, aerobraking bodies, earth return shields, or even 3D printing of spare parts and equipment out of regolith metals. All of that is possible. Now you ask, why bother? Well, Again, I'm using a historical analog. But what you find is that this is a common problem in nations that do exploration. In the early expeditions to the New World, a serious problem was basic support: food, ship repair, crew replacement. This is the whole gear ratio problem. If you try to do your exploration of the Caribbean based in Spain, what happens is that you use a lot of your consumables getting over here, and so that limits your range and viability in your explorations once you're here. The very first thing Columbus did in his first expedition was he left 30 guys behind to found a colony and start producing food so he could extend his reach the next time. The second expedition, he brought over 1,000 colonists to do the same thing. Of course, they didn't run off and grow food. They went and interacted with the natives in probably less than helpful ways. But you find that all the European exploring countries essentially did this. They quickly established advanced bases to provide in situ resource support to support their exploration goals. And for instance, Havana was founded basically as a central supply hub for Spanish expeditions in the Caribbean. And all the big Spanish expeditions left from Havana. That's where Cortez left from, not from Spain. That's where Cortez left from to go to Veracruz and interact with the Aztecs. Manila served that role in the Far East. And so advanced bases are critical. Every European exploring country had them. So New England, that was what the English, that was developed as the English base for the English possessions in the Caribbean. Goa for the Portuguese in India. Cape Town and Java for the Dutch. All of them had these advanced bases. All of them used ISRU because they recognized you can't do exploring on the end of a very long logistical trail. So science questions for Phobos and Deimos exploration. We're going to need to know the composition, and that relates back to the origin. And that directly feeds into the potential for resources. The structure, internal structure, whether it's a rubble pile, probably is. But are there big internal voids? What's the structure of the materials? What's the depth of the regolith? Are there any resources at depth? Do you have, for instance, water ice surviving at depth? Probably not, but we need to find that out. What are the regolith properties? The depth and particle size of the regoliths, the angle of repose and compaction, and of course the age and history. And this gives you a measure of the impact flux and history and the conditions in Mars space. So it represents a big store of knowledge that we will need to access in order to do smarter exploration. And that feeds into the strategic knowledge gaps. All of these things are SKGs that are critical to know to further our exploration of Mars and also Phobos and Deimos. Composition, whether they're organic or volatile resources, how can we exploit these resources, what are the geotechnical properties of the surface, what's the physical nature of the regolith, what's the structure, rubble pile, coherent object. For surface operations, what's the particle size, thermal properties, hazards, angle of repose? What kind of docking technologies do you need? What kind of effect will microgravity have on the surface operations on Phobos and Deimos? How do you handle materials in microgravity? How do you build shielding material? How do you extract the kind of resources you want from the material that's available? And what are the hazards in Mars space? Are there debris hazards? Do you have dust bands? And what are the radiation hazards in Mars environment? So fundamentally what we've got is a lot of questions. And I think this course will provide a few of the answers and also more strictly define where we need to be to get more answers. And so I'm looking forward to this adventure. I'm looking forward to learning a lot from our speakers. And I'm looking forward to learning a lot from our students and their questions. So thank you very much. And do we have more questions?
Yeah. So just do this.
Okay.
So it seems like there's a little bit of confusion about the density porosity question. So someone says H2O is less dense than the rock, so it should decrease the required porosity. So I think there was just confusion about whether it was ice with voids or ice as the voids.
Well, a void, by definition, has zero density. So you would need fewer voids if you had no water. If you have water, you need more voids because you're filling it up with something that has positive mass.
Okay. And Umberto has a comment. He says, relating to the albedo, only a small fraction of Mars surface material is needed to raise the albedo from the typical D-type to 7%, assuming 35% albedo for Mars surface.
Yes, that's true. What that small fraction is subject to discussion.
And then as a follow-up to the landslides filling in question, sorry, it's a very small window here. Leslie says, it's likely that additional views could resolve the question. Usually mass wasted material is less dense than the original material to some degree.
Yeah, I would agree with both those comments. It's just hard for me to tell.
And then we have, so if it is hard to get the albedo down, isn't capture of a dark object the most valid hypothesis?
Well, it is to some. This is a controversy because there are real problems to the physics of capture. And I think I will defer to Joe Burns and Robin Knupp that question. And I think the issue is, how likely is it to capture in this particular configuration? And the configuration is telling us something about the constraints of capture. It may be that it's more possible than some think, or maybe it's a very difficult requirement to overcome. There's lots of analogies in geology of people that said that something cannot happen, and then it turns out that, of course, it has happened, and the problem was that nobody had figured out how to model it. But I personally think that the low albedo is a pretty solid constraint. But I have no idea how this capture occurred, and I will defer to the experts in telling me that it's hard to do.
Berto also says, see his previous comment about albedo, which I just now read. That was much earlier in the talk. Okay, we have, I'll do one more here, and then maybe we have some in the room. Given constant bulk density and assuming constant grain density that is greater than ice density, the required porosity should go down. Oh, I guess that's the follow-up to there's just some confusion about, I think there's just confusion about generally there with that question.
Okay, well, I'll take a look at it, and maybe I can respond in detail via email.
Okay.
Because it's hard for me to do that in my head.
Yeah, it's fair play. There's a few more here, but do you want to take some in room?
Oh, sure. Let's start around the room on this end, especially if you're not looking at me. Question.
If you do want to ask a question,
yes.
Unmute the speaker closest to you.
Okay. So unmute that one. Leosh?
Okay. Okay, it's basically more a comment or question to the porosity.
Okay.
So, what I believe is that ice is not a pack of ice that you have in the material, but it's more rather mixed within the minerals and as how do you call it, impurities.
So this, you're talking about structurally bound water in the crystal structure, and that's common in various kinds of phyllosilicates, essentially clays. And given the location of Phobos and Deimos in the inner solar system and the relative heat that's available there, you're well within the frost line. That might be the way that any volatiles survive in that environment, is as structurally bound water in clays. So that's a possibility if you are capturing these things.
Because then you wouldn't have the density of ice. You wouldn't be able to calculate it as if you have a pack of ice.
Well, yeah, it would be. Yes, it would be different. I think the issue there is that you're looking at relatively low density phyllosilicates to begin with. Because the reason phyllosilicates are low density is that a lot of their volume is taken up by things like OH chains and water. And so that's a low density input to begin with.
Okay. Okay, so this is a question from the class at Brown. This little box is so little. Okay. Okay, we know that rubble pile asteroids, e.g. Itokawa, appear very blocky with thin or absent regolith layers. Does that apparently thick regolith on Phobos or Deimos suggest a more coherent internal structure despite their low densities?
I would say no, because of the unique environment that Phobos and Deimos find itself in. Basically, you can easily have a rubble pile where you tear the whole asteroid apart, but if you haven't accelerated that material fast enough, it's going to be retained in the Mars space and reaccreted. And the fact that you have a very relatively fine, not very blocky surface, I think speaks to the fact that a lot of the fine material is retained in Mars space and doesn't get a chance to wander off.
Okay, so we have another one. Is there a specific meteorite thought to have come from Phobos?
Is there a specific meteorite that is thought to come from Phobos? No. The problem is we still don't know quite what to look for. There are various kinds of carbonaceous chondrites that seem to be dehydrated, but there's no compelling reason to suggest that they're from Phobos or Deimos. Okay, more questions around here? Yes, sir.
So before you showed a slide with the slightly more bluish and reddish portions of Phobos.
Yes.
And I was wondering, it looked like the bluish region seemed to be oriented around like one hemisphere. And I was wondering if that told us something about the reaccretion of regolith in its orbit in Mars space.
I think the story there is maybe, and we'll talk about that more extensively as the semester goes on. The nice part about giving the introduction is I can push the tough answers off on other people. So, yes. More questions? Go ahead.
Do those kind of striations on the surface of Phobos, do those, pardon me, speak to anything about the structural integrity of the surface?
The short answer is yes. The long answer will be the subject of several talks. So I think that that's telling us something about what's going on the interior and the surface. And of course, it tells us a lot about the roughness of the surface. Stay tuned.
All right, so I don't remember which one, there was a hemispheric crater.
Yes, on Deimos.
And
well, they both have hemispheric craters, so, but Deimos is actually a larger portion of the object than the Stickney.
And
impact.
because they're in the Mars gravitational field, that all of that material doesn't leave.
Well, yeah.
So do we see where that could have gone?
Well, since the material hasn't left, I think what we're looking at potentially is that a lot of it got reaccreted to Deimos. And maybe the reason why you have such a subdued terrain is because you've kicked off a great deal of material and then reaccreted it. Again, that's one of the issues that I will slough off on my betters throughout this semester. And I think you should remember all these questions for these future talks, because they're good questions. Sure.
So still talking about these enormous craters on both moons, there must have been an enormous amount of energy involved. Does that speak to like the strength of the asteroids? Like if they're porous rubble piles, it seems like they would not be able to withstand. Well,
actually, that's a very good question, and I would urge you to try a simple experiment. Try hitting a hard ball with a bat and a pillow with a bat. And what you find with rubble piles is rubble piles are enormously energy dispersive. Rubble piles are a lot like hitting pillows. And so these things will absorb more energy, because what happens is essentially you take a lot of that energy and you're essentially dissipating it with friction as you're moving that shock wave through a loose body. And those things don't propagate shock waves that well. So one of the very first pictures of asteroids we saw was of an asteroid. I'm blanking on the name of the asteroid, but it had something like 5 impact craters, each one of which should have been enough to destroy the entire asteroid. But these craters not only did not destroy the asteroid, they existed right next to each other. They essentially didn't disrupt the other crater. And so they were so enormously energy dispersive. And I think that's a feature of rubble piles. And so rubble piles actually last far longer than coherent objects.
Okay, a couple more online questions.
Sure.
Recording fast here. Are Phobos and Deimos thought to have originated via the same type of formation?
Probably, because their albedo is similar. But once again, they end up on opposite sides of the Mars geosynchronous point. So their orbital evolution is telling us something, but I'm not sure what it is.
What is considered the youngest impact crater on both Phobos and Deimos, and what is their, i.e. the crater's, albedo compared to the bulk satellite's albedo?
That's a Nico question, and you'll have to ask that question next week. And so if Nico is listening, he needs to answer that question, because I can't. But he can answer it next week in his talk. Okay.
It just says, how do they provide the shielding against the space radiation?
Mass is a pretty good shield if you have enough of it. And so the way simply being on the Mars side of Deimos is going to shield you from 180, the solid angle of half the sky, because Phobos is between you and the rest of the sky, and 40, the solid angle of Mars, is going to shield you from a chunk of the rest. And what you can do is you can dig yourself in one of those grooves, for instance, and cover your habitat with regolith and provide more shielding that way. The other thing is that if Phobos is, say, rich in hydrated minerals like phyllosilicates. Those things provide fairly good stopping power. Low atomic weight elements have an advantage. And so using that as shielding material would be good.
Umberto says Matilda.
Matilda, yes, thank you, Umberto.
So we have another question from Leslie. Does the energy dissipation of Phobos' orbit and the energy gain of Deimos' orbit indicate anything useful for their relative dates of capture or formation?
That is a Joe Burns question, and I will defer to Joe Burns. This is a great place to be because I can push all the tough questions off on someone else. I would say the answer is yes, and I'm looking forward to Joe's answer.
Okay, Brown asks, what future missions are being planned for Phobos and Deimos?
Well, there are 3 discovery proposals right now, and I believe those are under review. The 3 are all remote sensing or landed package missions in some fashion, and there are other missions that are being muted by other organizations. There's discussions with European missions and potential Russian mission and so on. But this is something that I think we'll defer in more detail to later on.
Okay, Stony Brook asks, should we expect to see impact melt on either Phobos or Deimos, more or less than on a solid body?
That's a good question. I don't know. You do find impact melt in various kinds of regolith meteorites and certainly in lunar samples. I think you'd probably find less because of the energy dissipative characteristics of the loose rubble pile.
Okay, it's been noted that there is also a Phobos sample return sometime in the 2020s.
Yes, thank you. The problem with future missions is that they have varying ranges of possibility or probability, and so I don't keep track of them as well as I should.
Brown asks, are the craters on Phobos and Deimos smoothed out? Sorry, they moved. Smoothed out in appearance due to relaxation of the regolith or due to filling by crater ejecta?
I think that's a Sasha Babzalewski question, and so I will defer it to him.
Okay, there's some typings, but if there's any in-room questions,
okay.
we could take those.
Yes.
On one of the slides, you showed some of the spectral measurements of the D-type asteroids and Phobos and Deimos, and it appeared that Phobos and Deimos differed by some constant offset. Was that a result of something physical, or are they within the range just to be considered?
I think the constant offset was just an offset put in for clarity of the the plot, and this is that's something that you need to watch very carefully during Andy Rifkin's talk, because he will show you these things in excruciating detail, and it will be very interesting. More questions? You must have a question.
Yeah. So my question is, you had mentioned that there was evidence on Deimos of something called dusty streaks.
Yes.
And I was just wondering what exactly is the significance, or what would be the implications if these did turn out to be those dusty streaks?
That's another thing that I could never understand a way that you could get dusty streaks in a vacuum. So I note that that some workers have talked about that, but I think that that's another question that we can ask one of the geomorphologists during the next several subsequent lectures. This is great. I can dodge almost every question. More questions? Yes.
So the main point here is resource utilization, and I saw a lot of conversation about identifying what the resources are, and a little bit about excavation. Has there been much consideration to actually capturing the resources once they're released? Because with the low gravity, low pressure environment, I imagine capture would be a more specific challenge.
Well, I think that there's a lot of work being started right now on small body ISRU. And part of that requirement is that you essentially excavate and recover this material in such a way that you can capture the stuff that you either cook or boil off. So it's not trivial, but it's something that people are very well aware of, and that there's a number of methods that are being worked on right now to deal with that.
It seems like the main implication then is how much, even if you identify useful resources, how much can you capture at once? So
well,
how much usefulness can you get?
That's a good SKG. Essentially what you're talking about is what is the yield per kilo of useful stuff. And the analogy, I think, is oil extraction. When the oil industry started, 3 to 5% recovery of the oil in any reservoir was considered pretty good. Now, people are routinely talking about recovering 70% of the oil in a reservoir. So, your technology needs to get better to meet the challenges. And we're working on that technology, and actually people in this room are working on technologies to do that. More questions?
Yeah, so we've got another one from why might the surface of Deimos have more boulders than Phobos? Are we looking at the Brazil nut effect, i.e. impact-induced granular convection, think Music-Ionitakawa, or perhaps rather increased boulder production destruction? How might the surface structures of these bodies be constrained by the presence or absence of such boulders?
I don't know. That's a good question, and I think that that's a good Ken Ramsey question.
So we've got one from...
So probably it was Ken Ramsey that asked the question. So.
We've got one from Stony Brook. Would you expect the unconsolidated regolith of Phobos and Deimos to space weather faster than surfaces of more solid bodies?
That's a very good question. I would think that unconsolidated regolith would have more opportunities to space weather because you would have more surfaces to weather. That essentially the available surface and the available volume for these chemical reactions would extend deeper into the soil and have more opportunity. So yeah, I would think they would weather faster.
See, if you
Good
could
thought.
answer all these questions, there'd be no point in the whole seminar then.
I guess so.
Okay,
But I'd be tired though.
Leslie Gersh weighs back in. Perhaps dusty streaks could be formed by very low cohesion, ice-cemented, carbonaceous dust composites that disintegrate upon impact. Not a very satisfying solution, though. Are there any other ideas?
Well, that's an exciting one anyway. I like it. But I can't think of anything else. It's hard to imagine that that you would get much dust movement on an airless body except by, non-Aeolian processes. So perhaps we could think of an electrostatic or an impact process that would do that.
Okay, this question is from Leo Enright from Irish TV.
Okay.
I seem to recall a Russian LPSC paper suggesting that the regolith could be so deep and dusty as to be a major challenge to landing, the pre-Apollo nightmare of sinking into the mare. What are your thoughts?
I think that it would be easy to do some compaction experiments and retire that risk. The way we retired it on Apollo was essentially sending a robotic spacecraft. We can do the same thing with Phobos and Deimos, but also we've learned a lot about how things compact, and I think that it would be possible to design an experiment to mimic that process. So yeah, it's a thought, but remember that what we found was that the impact process not only generates fine material, but it also consolidates it at the same time on the moon. And although this environment is different, my first guess would be that there would be a consolidation process as well as a fluffing process.
Several people also note that boulders are sitting on the surface.
Yeah, that's a good point. I should have remembered that. That's a good thing about having lots of other experts online.
It ain't all fluff.
It ain't all fluff, that's right.
And then the dusty streaks look similar to tracks left from a rolling rock, perhaps due to impact events.
Well, that's a possibility. That is something I will leave for my colleagues to address. More questions in this room? Yes, sir.
Just had a comment. Wouldn't being in a microgravity situation also mitigate the effect of sinking in the surface? It seems to me that maybe not as big of an issue.
I think that's a good point. The idea would be that you just don't have as much normal force coming down and pushing you into that fluffy material, if there is fluffy material.
Snowshoes might be more effective.
So you could develop Phobos snowshoes. Yes, sir.
Since Phobos and Deimos have been this close to the sun for a very long time, would the volatiles have been removed from the outer layers, or do you think there could still be volatiles pretty close to the surface?
Well, it depends on what you mean by pretty close to the surface. I think that given the fact that these things have probably been rubbleized and turned inside out any number of times and reaccreted in Mars orbit, that things like ice would probably be tough to survive. But you don't know, fundamentally. That's just my own gestalt on this. However, you have lots of evidence of ices surviving in inner solar system bodies. The Tagish Lake meteorite ended up arriving on the surface of the Earth with ice intact in the interior, and it managed to do that after being in the inner solar system for some time and passing through atmospheric entry. So one of the nice things is that rock is a really good insulator, and really fluffy rock is a great insulator. And if you have volatiles at some depth, you have a fair amount of insulation around them. And so it's possible to survive for a long time. But what I would defer to my experts in thermal physics.
So someone notes that you have this huge radiator pumping lots of heat onto the moons, i.e. Mars.
I.e. Mars, yes. And so on one side, yes.
One side.
Only one side, yes, because they are tidally locked. So fundamentally, I don't know. It's something that I think we have to look at carefully, and it's one of these knowledge gaps that we'll have to fill in some fashion. More questions?
Multiple attendees are typing.
Uh-oh.
Is there any more in-room questions while we await?
We have a moment for an in-room question or two.
If there are any online questions that I didn't read, can you type those again? They're coming in quick there for a bit. Okay. Speaking of tidal locking, are there any surface differences between the Mars-facing side and the back side of either Deimos or Phobos?
I'm going to have to defer that question for the next several lectures. I don't think I could answer that in a thorough fashion. You are plumbing the depths of my ignorance in many ways. It's one of the reasons why I wanted to do this course, was to learn about all this stuff.
Multi-lecture spanning question. Okay. Any direct evidence of polar migration and/or rotating the tidally locked face on any Mars satellites?
That's another one I'll have to defer because I don't know. This is a very humbling experience.
Okay, maybe that's all.
Well, I'm looking forward to the next to all these lectures, because the audience has lived up to my best expectations of interaction and good questions. And the standard I have for questions is when I'm not able to answer all of them. And you've managed to exceed my expectations. So keep at it.
Okay, well.